Hello everyone, welcome to the OneClass channel. My name is Millan and I am a software engineering student at Carleton University in Ottawa, Canada. Today, I will be going over some commonly asked physics questions at both the high school and college or university level. If you're interested in getting some help with your homework or if you're interested in tutoring, check out the links in the description below. Cool, so I'm gonna switch over my screen real fast and we can start this physics experience. Cool, so let's get this party started. Okay, so the first question that we got on the menu today is asking us, we have two identical capacitors that are connected in parallel to an AC generator that has a frequency of 660 Hertz. That produces a voltage of 24 volts. Okay, the current in the circuit is 8 amps. Now we have to find the capacitance of each capacitor. Okay, this is a pretty cool question. Let's first start out by drawing out what this circuit is. So it said two identical capacitors that are connected in parallel. So here we can draw that out by doing something like this. Okay, so this can be capacitor 1, this can be C. And this can be capacitor 2, that's also C. And they are connected in parallel like this. Okay, parallel capacitors, exactly what they look like. And we have a AC voltage source. So AC voltage sources, typically you draw them like this. And we know that this is going to be 24 volts. It's going to have an AC frequency of 660 Hertz. 660 Hertz. And and the current going through this whole circuit is 0.8 amperes. So let's call this I is equal to 0.8 amps. Okay, now we're trying to find values of capacitors. Okay, so this is a diagram of all the necessary information that we can extract from the question. Now we can make some simplifications to make our life a little bit easier. So here I've identified a situation here. In this red circle we have parallel capacitors. Now, parallel capacitors, the way that you get like an equivalent capacitance out of them is pretty similar to how you do series resistors or series inductors. So, for a parallel capacitors, this is the equation. The equivalent capacitance is simply all the component capacitances Ci added together like this. Okay, so in this case CEQ, so if we were to compress these two capacitors into a single capacitor, we would just get 2C. Okay, nice and easy. So let's redraw the circuit. So let's redraw knowing CEQ. Okay, this should be nice and straightforward. So our voltage source is going to be the same, as well as our current also going to be the same. So we're going to have our AC voltage source 24 volts at 660 Hertz. It has a current through the circuit 0.8 amperes. That would be I. And here we have CEQ. I'll write CEQ, but we also know that this is equal to 2C, and we're trying to solve for C. Okay, so the question, what we have here is they use reactance, but in my opinion, I feel like it's better to use inductance, because inductance will be valid for when you also have resistors in the circuit at the same time, but reactance would not necessarily be appropriate if you had both storage elements, like if you had resistors and inductors or resistors and capacitors, you would need to use inductance for that. So reactance is very specific to when you only have storage elements, meaning inductors and capacitors. So let's find the impedance. Let's use impedance instead because it is more universal. Okay, so we need to get impedance. Get impedance of capacitor. And for those of you who are maybe unfamiliar with impedance, impedance is essentially like resistance but complex. So impedance is basically just resistance in complex form. Okay, cool. So we know that impedance of a capacitor impedance looks like this. So Z, we use Z or Z. In Canada, we say Z for the last letter of the alphabet. But ZC, or the impedance, Z or Z, represents impedance. I'm going to say Z because that's what we say in Canada, but a lot of places also say Z for that. Interesting quirk of language. But the equation for that, to calculate the impedance of the capacitor, is 1 over J omega C. And omega is the omega is angular frequency. And J is the complex term. And it's not really relevant for this particular circuit. So, but, just keep in mind that it is there. You do need to be kind of familiar with the complex numbers, but just keep in mind that this is the complex term. Not really relevant. For this particular circuit. Okay, so the angular frequency, we know that this is 2 pi times F. And F is equal to 660 hertz. So our omega term here, this has got to be, what we have here? We're going to have 2 times pi times 660 hertz. Now I'm gonna put that into my handy dandy calculator because my quick maths are not that quick. 2 times pi multiply 660, and we get this is equal to 4146.9 radians per second. Okay, so let's substitute in some of these numbers into our equation here. So I'll actually switch up the color. So blue for capacitance. So now when we actually want to find the ZC, the impedance of this circuit, which is really just the impedance of the capacitor, we're going to do 1 divided by J, multiply that by omega, which is 4146.9 radians per second, multiplied by 2C. Right? Because that's the equivalent capacitance of every capacitor in the circuit. Okay? So we definitely cannot forget that 2 term. Okay? So, send that into the calculator and see what we get. It's really just multiplied by 2. So we get Z over C is equal to 1 over J times 8,293.8 farad radians per second. The unit is not super important. I'm just writing it out to be formally proper, but you know, if you're rushing, you don't really need to focus on that. Okay, now this is the impedance value that we're going to use. Okay, so we know that since impedance is basically just resistance in complex form, we know through Ohm's law. Oh wait, I got to attach the C at the end of here, right? Because the C is the variable that we're trying to solve for. This is our target variable. Okay, now we know from Ohm's law, I'll put this in orange. Does that appear well? Yeah, okay. Ohm's law also applies for impedance and AC voltages and currents. Okay, but we'll need to find the magnitude of them. All right, so the magnitude of this, so since, oops, I'll switch back out to blue because it's kind of more related to that. So since impedance is a complex number, convert to magnitude. Okay, now the magnitude here, it's very so you would do like real squared plus imaginary squared, all under the root. It's definitely got the same type of energy as good old Pythagoras. But since we just have the imaginary part, so the j is what's associated with the imaginary part. Whoever has a j factor attached to them, that's an imaginary term. Okay, so in this case, our ZC impedance magnitude, and magnitude is typically represented by like absolute value bars on either side of your variable. So once we surround it by that, well, in here for our ZC, our real component is just 0, so it's just gonna be like square it and then square root it. So for us, our ZC, our magnitude of ZC, is just gonna be the same, but the j is gonna disappear because, as we know, j is equal to the square root of -1, and when we square it and then neutralize it, like it's really, honestly, just avoid using j like period inside of your magnitude calculations. Okay, because you actually don't want to use your j at all in that calculation. You just take like the term associated with j. Okay, so for us in this case, this is really just going to be the same as 1 over 8 to 93.8 C. Okay, now we know since Ohm's law is telling us basically that we have V equals I Z. Remember, impedance, like resistance. And we be trying to solve for C here. And C is a component that makes up Z, so we want to isolate Z. So V over I is equal to Z, and we know that Z is going to be equal to 1 over 829.3.8 C. Okay, so now if we're trying to isolate C, isolate the C. You see what I mean? We will bring the C to the other side, and everything else can stay here. So C is going to be equal to I over V, and down here is going to be multiplied by 829.3.8. And subbing in our values, we get I is equal to 0.8 amps. That was a nice easy number, 0.8 amps. Our voltage is going to be 24 volts. And then we had this other term here of our 8,293.8. And then we math this out and we will find our capacitance. And that will be awesome. So let's ask our calculator to figure that out for us. 0.8 divided by 24 times 8293.8. And the result that I got was 4.02 times 10 to the negative 6 farads. Remember, capacitors always have the unit of farads, and that would make perfect sense here because I didn't write the unit here attached to that 8,000 term, but we know that it was like it was radians, farad, radians per second. Yeah, so I'm sure that would all work out, and we come to farads. And another way that we could write this is we can convert that to a micro farad. Whoops, I guess that'd be more like that. So we have C is equal to 4.02 microfarads. And that is a pretty reasonable answer. A lot of times you'll see capacitors that are measured in microfarads. So based on the magnitude of it, it feels like it could be a reasonable value. And it would seem that our result from the junior tutor here looks good, and we came to the same conclusion, and that's awesome. So just as a recap, we want to first simplify our circuit as much as we can, and then we found the impedance of the capacitor. Once we had the impedance of the capacitor, we could use that in Ohm's law, knowing the voltage and the current, and we used that and we could solve for C, which was the only thing that we needed to solve, and that's the value of the capacitor. And we realize now that we have to have 4.02 microfarads. That would be the only capacitor value that can make this description of a circuit valid. Okay, so here the above solution is good. That's awesome. Great stuff. Great work. Cool. Okay, so the next question that we got on the menu today is asking us, a horizontal force of 159 newtons pushes a 20 kilogram block up a frictionless incline that makes an angle of 35 degrees. I'm going to assume that A just means like degrees, with the horizontal. Now, what is the normal force? Okay, well, before we even start asking questions about this situation, let's draw a diagram for this situation because just purely word descriptions are pretty tough to deal with. So I like drawing diagrams because they can really help us. Okay, so it's saying that we have a block on a frictionless incline. I feel like we can represent that pretty well with a triangle like this. Okay, looks pretty good. And we have a 20 kilogram block. Let's draw that. $20 kilogram block. Okay. And nice. And it says that we have a 159 Newton force that is perfectly horizontal. Okay, so it's not going to be on the same angle as the incline itself. It's going to be perfectly horizontal. So it's going to be something like this. So 159 newtons, whoops, not K, 159 N newtons, and we're also going to have, what's another detail? We have a 35 degree angle here. 35 degree angle, and let's actually draw a free body diagram of this situation, or let's draw like the other forces of interest here. So we know that this 20 kilogram block here, well, things are heavy, and with the power of gravity, they fall. Gravity will typically force you to fall because gravity is a force, and this 20 kilogram block is definitely going to have a weight force of gravity. So this would be like, let's call that W for weight is equal to mass times the gravitational acceleration. That's one of the forces that's also going to be on here. It mentions that the slope, the incline is frictionless, so we have no friction force. That's nice and convenient, one less force to worry about. But how come this block isn't falling through the ramp? It's because the ramp has a opposing normal force, and we have to consider that. And that's also the thing that we want to that's another thing that we want to solve as a part of this. The first part of the question is trying to tell us what is the normal force. Okay, I'm just going to draw that in a different color so it's very clear and distinct. And one interesting thing about the, oh, that's not a different color. One interesting thing about normal forces, so let's call that Fn for normal. They always have to be perpendicular to the surface. Okay, so this is perpendicular to a ramp. Which means it has a 35-degree angle from the vertical. So you see how the ramp has 35 degrees from the horizontal? Well, this one is 35 degrees from the vertical. You know, that's kind of a rule if things are perpendicular. Okay, so let's actually draw this free body diagram again, but like off the ramp. Okay, I'll do this in black. I can kind of imagine this as a particle. Yeah, okay, so here we have Fn. (35 degrees towards the right of the perfectly vertical, so this would be Fn. Here we have mg. And here we have our perfectly horizontal force of 159 newtons. Okay, now it might be a little bit more convenient if we put all of our forces in an axis that is like you know, along the slope. Okay, so if we have our x and y axes like this, this will make our calculations much simpler. It's still possible if we don't make an alternate axis. It's just going to be a little bit painful. Okay, so knowing this is our redefined axis, we know that our normal force is going to be perfectly in the y direction. So actually, I'll redraw this free body, or I'll make some adjustments to our free body diagram. So if this is our y direction, and this is our x direction, like that, just as it appears in the diagram, we could see that, well, we would have this situation here, and this angle here is 35 degrees, and this angle here is let me think about this for a moment. So let's do the angle like this, and we will have okay, so if it's perfectly horizontal and we want to resolve it up the ramp, we're gonna have this angle as 35 degrees. It has to be 35 degrees because pretty much what we have is like the force is like this, the ramp is like this. So this angle 35 has to be the same as this angle 35 up here. Okay, so that's pretty much where all of these angles come from. Okay, now we know that the force along the y direction of this situation has to be 0, the net force. And the reason for that is because, well, we know that it's only going to slide up the hill or down the hill. So with our tilted axes right here, we can only have x direction forces that are not perfectly neutralized. So if we wanted to do the sum of all y forces, we have to equate them to 0. If the y forces were not 0, it would be like lifted off or pushed deeper into the ramp itself. And we're gonna assume that like the ramp does not like curve or deform in any way that would allow things to be pushed into it. So we have to have a 0 y force. Okay, now what are our forces in the positive y direction? We have Fn, and there's no need to have any angle associated with it. Okay, now let's look at mg. Okay, so now mg is going in the negative y direction, so we got negative. We're going to have mg, and we're also going to multiply this by a factor of cos 35. Okay, the reason why is because we want the this component right here. So this is mgy and mg x. Okay, that's a little messy. I'll redraw that. Okay, so you see the actual mg, we can break it into components, and the components are related to our tilted axes. So we only want the y components of the mg. So to get that, we need to multiply in cos 35, which is about maybe 80% of it. Okay, and that seems fairly reasonable. Okay, now since our pushing force was perfectly horizontal, this is also going to be pushing it into the ramp a little bit. Okay, so there is going to be a y component to the perfectly horizontal force, and the y component is going to be sine 35. You see, like, this is pretty much the same as saying this angle is like, or this force is something like this, something like this. Okay, so we only want the one that's along the y, and that's got to correspond to sine 35. Okay, so that's going to be, let's draw that in, minus 159 Newton times sine 35 degrees. Okay, awesome. So now let's sub in our m value. Our m value is 20 kilograms. And our g value is equal to 9.81 meters per second squared. I use 0.81. You could use 9.8, but here in Canada it's 9.81. Closer to the poles of the Earth, you'll have faster acceleration, and closer to the equator, you'll have slower acceleration. So you might, in your local area, you might have a different g value, but we'll just use 9.81 for here in Canada. Okay, cool. Let's sub these in, but first let's isolate Fn, because that's going to be our target variable actually. Okay, so Fn, and then we're going to bring these two terms to the other side, and let's sub in m and g. So we're going to have m is equal to 20 kilogram. Multiply that by 9.81 meters per second squared. Multiply that by cos 35 degrees. And we are going to also add, now it's going to be this term, so the 159 Newton term, but when we bring it to the other side, it's going to be positive. And I'm a positive guy, so let's put that in there. So we got 159 newtons multiplied by sine 35 degrees. Okay, and once we do this calculation, this will give us the normal force, and then that'll be one part of our question done. So let's set this in. So 20 times 9.81 times cos 35 degrees. Make sure your calculator's in degrees. If you do it in radians, big ouch, I'll tell you that. Okay, so plus 159 times sine of 35 degrees, and our final result here for the normal force is equal to 251.92 newtons. Okay, awesome. So this would be our normal force. Normal force on ramp. Awesome. Okay, so that is part A of this question finished. Super cool. Okay, now the second question is asking us, what is the acceleration of the block? Okay, so this kind of ties into what we were doing previously. I'll actually I'll copy down this whole diagram so we don't gotta draw it in again. Because what we're going to be doing here is we will be doing pretty much the same thing that we did with in the y direction of our tilted axes, but we're going to do it in the x direction. Okay, and that's going to give us a force, and then once we get that force, we can divide out the mass and find the acceleration up the ramp. Okay, so here let's paste that in. Okay, so this was our free body diagram of just the forces that correspond to our ramp situation up here. Okay, cool. So now we want to find, there is only a net force in the tilted x-axis direction. Cool. So how we're going to set up our equation is we're going to want to do something like this. Okay, so we want to have the sum of all x forces in here is going to be equal to the mass of the thing multiplied by acceleration in the tilted x-axis. Okay, now previously we set up our equation differently, so the sum of all Fy was equal to 0, but that's because there's no acceleration in the y direction. Like if my arm is a slope, there's no acceleration this way, there's only acceleration this way. Okay, so that's why in the x direction we're going to have a ma instead of a 0, which is going to be the sum of all the x direction forces. Cool. So let's take a look at all of our forces and see who has a x direction contribution. So Fn, well, Fn is strictly and purely in the y direction, so that's going to have no effect on the x direction axes of force. Okay, so let's consider our gravity. So you see mgx, that appears to be it's going to be mg, right? But we want only the x components about it, and that's going to be sine 35 degrees. Okay, you can kind of see how that works. Think back to your trigonometry. If you just want to get like a component from an actual force. Okay, so we're going to have, and that's in the negative direction, or that's going to be in the positive direction. So the way we set up our axis is we have positive down the ramp, negative up the ramp. Okay, so it's positive down ramp, negative up ramp. Okay, so down the ramp, what's the weight going to do? Gravity is going to try to push you down the ramp, so it's going to be a positive. So it's going to be positive mg multiplied by not cos, in this case it's going to be sine 35 degrees, and here we're going to have now the second thing that we need to consider is going to be the 159 Newton force, perfectly horizontal. In this case we want to get just the x component of it. This is going up the ramp though, so it's going to be a negative term, negative, and then we're going to have the 159 Newton, And what term do we have to multiply into here? Cos 35. Okay, and you can see kind of how the angle works. We want to get we have the hypotenuse, and the angle, we're trying to get the adjacent. So with SOHCAHTOA, we can do it this way by doing cos 35. Okay, so let's isolate AX. AX, and M is equal to 20 kilograms. Yep. And G is still going to be 9.81 meters per second squared. And when we do this, we'll have AX equal to 1 over 20 kilogram. So that's 1 over M multiplied by 20 kilogram times 9.81 meters per second squared multiplied by sine 35. And this is minus 159 newtons. Multiply that by cos 35. Okay, and we'll ask our calculator what this is, because mental math is tough. Okay, so we're going to have 1 divided 20. 1 divided by 20, and that whole thing is multiplied by 20 times 9.81 times sine of 35 degrees, and that whole thing is subtracted by 159 times cos 35 degrees, close those brackets. And my final acceleration calculation for this is negative 1.61 meters per second squared in the x direction. Now keep in mind, we've said that negative is going up the ramp and positive is going down the ramp. So this is going to be up the ramp. So with the given forces, the block will accelerate up the ramp at 1.61 meters per second squared. Okay, that's going to be our final answer, and that resolves the second part of our question, and that's the final part of our question, so we can call it a day. Okay, now I think I've seen a question questions similar to this in like my first year of university or first year of college when I was doing engineering. So it is fun stuff. They're just like, the main key here is that you want to set your coordinate axis to be along the ramp, and then resolve your horizontal and gravity forces to be along those tilted axes. It's going to be way more difficult to try to do it with like a regular XY being like perfectly horizontal, perfectly vertical. That's going to be way harder. Okay, so there's no above solution. Is no given solution. Okay, cool. So yeah, that question, that's that. Okay, cool. So the next question that we got on the menu today is asking us an alpha particle. And an alpha particle, if you are unfamiliar, is just a helium ion. So it's just 2 protons stuck together. That's what a alpha particle is. There on my periodic table, it's on the so I'll open up my screen. So here on my periodic table, on the upper right corner there is there's helium. That's what it is, and that's what an alpha particle is. And okay, so it's telling us it has a mass of 4u and moves in a circular orbit of radius 7.5 centimeters in a uniform magnetic field of 0.6 teslas, where the magnetic field is perpendicular to the orbit plane. And that has to be the case. Now we got to find the speed of the alpha particle, the period of the circular motion of the particle, and the direction given this diagram. Now, this diagram is a little bit sketchy because that's it should be a perfect circle, but we'll just pretend that's a perfect circle. Okay, so let's first thing that we want to do is we want to extract all of the important information out of this question. Okay, so we got an alpha particle, and we know the charge is going to be positive 2e. Okay, so we know that our charge, which is typically represented with the letter Q, is equal to positive 2e, which is equal to 2 times 1.6 times 10 to the negative 19 coulombs, which is simply 3.2, it's positive 3.2 times 10 to the negative 19 coulombs. That's kind of a number that I like to memorize. Not that you really have to, it's just, why not, you know? Okay, so its mass is going to be 4, it's the atomic mass of an alpha particle is 4, and we know that the mass of, because it has 2 protons and 2 neutrons in the alpha particle, so it's just going to be, our mass is just going to be 4 times the mass of a proton, because protons and neutrons are pretty much the same mass. If you go really deep, they're not, but they're pretty much the same. For most people unless you're going really deep into nuclear physics, you can consider the mass of a proton and the mass of a neutron to be equal. Okay, so our mass is 4 times the mass of a proton, which is 1.66, multiplied by 10 to the negative 27 kilogram. Gonna do the math real fast. 1.66 times 4. So this is gonna be 6.64 times 10 to the negative 27 kilogram. And it's always good to keep your units in base SI units, because it'll make your calculations a lot easier. Okay, it moves in a circular orbit of radius r equals 7.5 centimeters. So r, 7.5 centimeters, and we can convert that centimeters into a times 10 to the negative 2. And that will just make things a lot easier, or you can just convert this to meters basically. So that'll just be 0.075 meters. Okay, just because we want to get base SI units, they work better. The magnetic field has 0.6 teslas, so B field. Why is magnetic field represented with B? Yes, that is why. It just is. So the B field, the magnetic field, is 0.6 teslas. And the magnetic field is perpendicular to the orbit plane, as we might expect. Okay, so these are our equations of interest. Now let's actually look up some more things about the circular motion of stuff, because we know that the force from the magnets, make this a different color to show that we're different things. So magnetic force on moving charge, so F as a vector, so FB, and that's for magnetic force. It's going to be Q times the cross product of the velocity and the B field, the magnetic field, and circular motion, centripetal force, centripetal force is equal to Fc as a vector is going to be mass velocity squared over r. Okay. Yeah, so knowing these, we can solve for B, and once we solve for B, we can or we can solve for v, and then we pretty much can solve the whole thing. So that's what the speed of the alpha particle is. We know that the magnetic force on a moving charge, any charge that moves in a constant magnetic field, is going to move in a circular path. And the same force, the magnetic force, is going to be equal to the centripetal force. Okay? So, to write that out formally, so magnetic force, centripetal force. So these two are the things that cause like these are the same force in this case, because the centripetal force is caused by the magnetism. It's just we have two different equations to represent them, and that's going to be quite useful. Okay, so let's write out what we have here. So and I guess we don't really need to worry about the cross product because it is just like a multiplication, because we are in a two-dimensional thing. It's just more formally it is the cross product. But you can just treat it like a multiplication for a 2D example like this. So we're going to have FB is equal to QVB. And that's going to be equal to the centripetal force, which is mass times velocity squared divided by radius. Okay, now we're trying to isolate velocity. Okay, so we can do that by dividing by sending. Let's just isolate the velocity by doing like we're gonna have. So we're going to have like 1 equals mv squared over r qvb. Okay, if we divide both sides by qvb. And what that's going to do is that's going to neutralize the velocity, which is, or it's going to neutralize a square. And then we can just bring everything to the other side except the velocity. So we're going to have r qb over m is equal to v. Okay, now what was our now we had all these values initially, so our r value was, oh, where did my mouse go? Oh, okay, so our r value was 0.075 meters. Our q value is going to be 2 electrons, but positive, so 3.2. So we're going to have 3.2 times 10 to the negative 16 coulombs. Then our B value, I remember that was 0.6 Teslas. And all divided by our mass, which was 6.64 times 10 to the negative 27 kilograms. Okay, cool. So let's send that into the calculator and figure out what the numerical result of that calculation is. So we got 0.075 multiplied by 3.2 multiplied by 10 to the power of negative 19. Oh, I should write, it looks like a 16, that should be 19. Okay, times 0.6. That whole thing is divided by 6.64 times 10 to the power negative 27. And the numerical result of that velocity is quite speedy. So V is going to be equal to 2,168,674.7 meters per second. Another way that we could write this is v equals 2.168 times 10 to the 6 meters per second, or we can say 2.168 mega meters per second, because mega is another way of saying a million. But this would be how we find the velocity. And is that a reasonable number? It really is a reasonable number, because these velocities will get very, very fast, especially when you have things that are that light. So even like the most minor force on something that costs, or something that's like 10 to the negative 27 kilograms, that's going to be extremely, extremely fast. So that does feel like a reasonable answer. Okay, so cool. This would be the velocity of the particle as it travels throughout the loop. That's awesome. Okay, now we want to find the period of the period of the circular motion. Okay, so let's do that. Period. Circular motion. Okay, so we know that the velocity of this thing is we have the velocity value, and we know that the velocity is going to be always constant as it travels in this circular path around the loop. Always got to be constant. So, and we also know that the radius is equal to 0.075 meters. 7.5 centimeters was the radius of this circle. If we know the velocity and we know the radius, we can figure out the circumference of the circle, and then no, that's just the distance that it travels. So, and every time is going to be the same. So knowing the velocity and the circumference, we can find the period. Okay, so circumference. Let's call the circumference CF. Now I'm not using just C directly because we do have like charge that we used previously, and I don't want the C for circumference to be confused with C for Coulomb, so I'll use CF instead. So the circumference of a circle is 2 times pi times the radius. So we have 2 pi times 0.075 meters. And this is going to give us 2 times pi times 0.075. We get 0.471 meters. So 41 centimeters circumference. Seems reasonable. Okay, so now if we do circumference divided by velocity, we will get the period. Period is often represented with t because it's like the time that it takes for you to do something periodically. Always be the same. So here we'll have 0.471 meters divided by 2.168 times 10 to the positive 6 meters per second. So you can see how the meters cancel each other out. The per second goes upstairs and becomes just regular seconds. And I'm expecting a very small amount of time because that is something very, very big. That is something very, very fast, traveling not a very large distance. So I expect a very small number. So let's do that. 0.471 meters divide by 2.168 times 10 to the power of positive 6. And our result for this is 2.17 times 10 to the negative 7 seconds. And another way that we can write this is 0.217 microseconds. So that's very fast. That's a very short period, but we would expect something like that given that the circle is 7 centimeters and we're traveling at millions of meters per second. We should expect a very small period. Okay, very quick. Okay, and now that kind of so this is going to be t, and that's going to be the second component of our final question, and that is that resolved. Cool. So the last question that we have is asking us, given the direction of the rotation, or we have to find the direction at which the positive charged particle is going to be moving in this loop. Basically, is it clockwise? Is it counterclockwise? Now, what we want to do here is, remember how our force was like our magnetic force, our FB, is equal to Q times velocity cross the magnetic field. Okay, so we pretty much we want to be using the right hand rule. So I guess all these vectors are not particularly you know, they're not useless, right? They're there for a reason. So we want our fingers to be going the same direction as V. So it's either clockwise or counterclockwise. We want our fingers to curl. We want our fingers to curl along the magnetic field. And where our thumb points is going to be the direction of the magnetic force. Okay, so if we wanted to start in a clockwise, make my camera a little bit bigger so we can kind of see what's going on. So if we're trying to go counterclockwise on the diagram like this, our fingers would be following V, so like this. Our fingers would curl. Basically, our palm is pointing along the B, and you see how the X's represent that the magnetic field is going into the page. If they were dots, they would be coming out of the page. So we want to curl in the direction that the B is going, so that's into the page like this. So we've going like this, and you can see that the B force, my thumb, which is supposed to be the direction of the B force, is always going to be towards the center. That would suggest that we're going to go that's the direction of the force that it needs to be, because it needs to accelerate you towards the center of the circle to keep you in that circular path. Okay, so it actually is going to be counterclockwise. Because if we were to go clockwise, our thumb would be pointing outside of the circle. So it would be right if it was an electron or a negative charged particle moving through the B field. We'd be going clockwise if it was a negative charge, but since we have positive charge, we're going counterclockwise. CCW. So we want our fingers like this. And they're curling towards the X's. And since the right hand, we have it like this. Thumb points towards the middle. It's got to be counterclockwise. Okay, so it's quite a long question, but quite a beautiful question as well. It ties a lot of subjects together, like magnetic force as well as circular motion and all that fun stuff. Super cool. There is no given solution. Okay, so the next question that we got on the menu today is asking us, what is the maximum angle that this ramp is going to be allowed to be inclined so that the box does not slide down the ramp? Okay, because if the box slides down the ramp, well, you know, they won't catch you slipping, and that's not great. So you don't want to be caught slipping. So what's the maximum angle that we can have? Let's actually draw our own diagram on this, because I can't draw on the OneClass image. But let's get it started here. So we have a 50 kilogram mass like this. 50 kg. Okay, now we have no idea what this angle is. We want to find the maximum angle at which this will not be slipping down here. Okay, and the only thing that is preventing it from slipping is the frictional force. Okay, so let's actually draw all of our forces onto this system. I'll draw the forces in blue. So we have the frictional force, which is going to be going up the ramp. And we know that this is going to be equal to the coefficient of static friction, which is given as 0.235 multiplied by the normal force. Okay, so this is going to be our frictional force, and that's the only thing that's preventing it from sliding down. So less normal force means less frictional force. Okay, and another force that is definitely going to be here is the force of gravity, which is going to be straight down. So that's Fg. And that is equal to mg, which is equal to what's the mass? The mass is 50 kilogram. Multiply that by 9.8 meters per second. And just to find that out quickly, so we have a numerical value, because the weight force is always going to be the same. It's never going to weigh less. No balloons attached to it, or nothing like that. Like, it's going to have a constant weight. So we got 50 times 9.8. We get 490. 490 newtons. Cool. Yeah, and the next force that we need is a normal force. Okay, our normal force will be like this. So this is Fn for F normal. And the normal force has to be perpendicular to the ramp. Okay, so this is perpendicular. Okay, awesome. So now another way that we can kind of handle this question to make things a lot easier is to have a tilted axis. Make that a different color so we can kind of have some connection on that. So tilted axes make math much easier. What I mean by tilted is you want to have them like this, so that they're pretty much in line with the ramp itself. Okay, now imagine this. Okay, so our F force is going to be perfectly in the x direction, in the negative x direction of these axes, and the Y force, which is the normal force, is going to be perfectly in the y direction. We only got one force that we need to make into our, we only have the gravitational force that we need to force to be changed. But if we had regular axes, like perfectly horizontal and perfectly vertical for x and y, we would need to adjust both the frictional force and the normal force, which is a little bit more difficult. So yeah, but to resolve the gravitational force to be in components that are perpendicular or parallel to the axes, we would just need something like this. So I'll put this in red. So you see these red arrows are perfectly in line or perfectly parallel and perpendicular to the axes. And we know that, if we draw them like this, we can show pretty clearly that those two vectors added together are going to be equal to the weight force. Okay, so let's call this FGY, and let's call this FGX. And if we have those, it will be a lot easier to deal with. And another thing that's important here is that the angle that they make here is going to be the same as the angle that is made over here with the ramp. Okay, so to prevent this from sliding, it's back to action here. So to prevent, angle, or nope, net force on tilted x-axis must be 0. Non-zero means slip in. Okay, so let's actually build an equation to kind of represent that. So we know that the sum of our x direction forces must be equal to 0. And we know that, well, if we have up the ramp as negative x, we're going to have negative ff plus fgx. Okay, so those two have to be equivalent to each other for this to be valid. Now we can rewrite these equations as we know that negative f of f. We can rewrite this as negative 0.235 Fn plus Fg times sine angle. Because you can see here from the diagram, from this little triangle section over here, for that triangle like associated with the gravitational force, if we want to get Fgx, which is down the slope, you can kind of see with some trigonometric magic that it's going to have to be the angle, right? So yeah, but we have no idea what Fn is. We're going to need to do the sum of all forces in the y direction to solve for Fn, the normal force. Need all forces in y direction to get Fn. Oh, bless you. Thank you. Must be 0, or else block would sink into ramp or float off of it. Which is certainly not something that we can really deal with. It's not sinking into the ramp, it's not floating off it, it has to be 0. So Fy is got to be equal to 0. So let's look at our diagram for our y component forces. Positive is like flying off the ramp, so we only have n of the normal force, which is in the positive direction. So there we have positive Fn, and we have a negative force in the y direction, and it's Fgy. And you can see here is going to be cos times Fg. So Fg cos angle. No idea what the angle is. We have to solve for that. Okay. So given that we have these two equations, we have a system of equations. We can solve for. Let's first solve for the normal force, and then we can keep it moving from there. So if we isolate Fn, Fn is equal to Fg cos theta, and Fg we know is 490 newtons, right? So 490 newtons multiplied by cos angle. Okay, so now that we have this relationship for Fn equals Fn, normal force, we can sub that into our previous equation for, so we'll sub this into our x forces equation. So here we have f of x is equal to 0, which was equal to it was negative 0.235 Fn. Add 490 newtons. That was the previous Fg. I'm just putting in the numerical value times cos. Was it cos up there? No, it was sine up there. My bad. times sine theta. And of course, inside of here, we can sub in Fn into here. So we have 0 equals negative 2.35. Whoops, not 2.35, 0.235. 0.235. And we have to sub in this whole thing for Fn. So we got 490 newtons multiplied by cos theta and plus 490 n, 490 newtons times sine theta. Okay, so let's bring that negative term to the other side of the equation, and let's actually multiply this in so we just have like single numbers. Okay, so 0.235 multiplied by 490 is 115.15. So we're going to have 115.15 newtons cos theta is equal to 490 newtons sine theta. And we're trying to solve for theta. Okay, so keep in mind that if we divide both sides by cos theta, and or what I'm trying to say here is that we know that tan theta is equal to sine theta over cos theta. Okay, so if we can get a cos theta in here, and then that's like cos theta or tan theta is equal to a number, and then we just do inverse tan, we can solve for theta. And that's my plan of attack here. So we're going to divide both sides by 490 and divide both sides by cos theta. So we're going to have 115.15 n divide by 490 newtons is equal to sine theta over cos theta, and that's equal to tan theta. And the numerical value of that calculation, 115.15, divide by 490, that's equal to 0.235. Hey, and that's exactly our coefficient of friction, which I'll get back to that. It's kind of some secret sauce here. Yeah, so given that we have this, we know that we can do theta is equal to arctan of 235. That's not cotangent, by the way. Arctan is a whole different operation. So we'll do arctan of 0.235, and the result of that is 13.2 degrees. So this is maximum angle before slipping. Okay, so 15 degrees, you know, that's pretty much flat with just like a little slope like this. Like it's not so steep. It's not so steep that you would you know, slide on it in the wintertime. But if you dropped a grape on there, it'd definitely be rolling. It's not super steep. But another key thing here is this is actually the definition of coefficient of friction. So like this whole process we showed is like how this was originally derived, and like if you get a type of situation like this on the exam, you're probably going to need to show your derivation. But this is the definition of coefficient of friction. Of coefficient of static friction. Now it's important to specify the difference between static friction and kinetic friction or dynamic friction, but this is the definition of the coefficient of static friction. This is the tan of the angle when thing starts slipping. Down ramp. Okay, so this is actually where these coefficient of frictions even come from. Now you could just, like, if you wanted to, you could just say, okay, well, the maximum angle, we can just take the arctan of this, but you know, the derivation is important. But sometimes you will need to calculate the coefficient of static friction yourself. Like, let's say you're trying to figure out a system like this, and let me see if I got any real life examples that I could show for this. So here I got a calendar. This can kind of represent a ramp, like this. So if I'm trying to figure out the coefficient of static friction of my calculator here, and I put it on like this, and of course I would want a better table, but if I had a protractor watching the angle I was raising it, the precise angle that this calculator just starts slipping, right there. Okay, I'm not sure if you can see it properly, but it is slipping. So it'd be like the protractor measured whatever this angle is, take the tan of that would be the coefficient of friction for my calculator. Okay, so that'd be an example of like why you need this, why this be useful in real life, because most of the time you're not necessarily going to know the coefficient of friction, and it also depends on the surface. So my calculator on that calendar might have had a coefficient of friction of a certain value, but my calculator on top of a block of ice, completely different coefficient of friction, right? Ice is pretty slippery, so it's going to have a much lower coefficient of friction. So yeah, you will typically need to find this in many different ways, but you know, it seems that the solution that we have here this is coming to the same conclusion, which is pretty cool. So okay, things are looking pretty good. They came to 13.2 degrees, so the above solution is good. Can be dangerous to use capital N as the normal force variable because it could be confused with the capital N for Newton force units. Fn, F subscript N is a more safe option. Okay, cool, awesome. Okay, so the next question that we got on the menu today is asking us about some equivalent capacitors. Okay, so this will be a nice and fun question. Let's get it cracking. Okay, cool. So the first question is asking us, what is the equivalent capacitance between points X and Y on the entire capacitor network? Answer in I1/4 F. I'm going to assume, so I did a little bit of background research. This is not a real unit. I'm going to assume that I1/4 F, this means microfarads. Equal to that, which is equal to 10 to the -6 farads. Okay, that'll be what I'm dealing with here. I think that might be like a technical issue, but let's redraw the circuit here. So typically I don't really like drawing voltage sources like this with capacitors because it can look a little bit too similar. I prefer to draw it like this. So we got 106 volts, and then here okay, this would be our first node in our equation right here. So here we got a capacitor that's 11 microfarads. Here we got 14 microfarads. That's connected to a 14 like this. there's another 14 like this. And over here we have 3 14s that are in, we got 3 14s in series like this. I'll just draw it this way. It really means the same thing. I know it's not perfectly the same as the diagram, but the circuit is perfectly equivalent. Okay, so it's another important skill to have, is to kind of know what circuits look like. And now it says, what are the equivalent capacitances between points X and Z, between points Y and Z? I don't see any Y's or Z on here, but I think what they really mean is like, if this was Y and this is Z, so equivalent capacitance of circuit. Okay, so these are, it's very similar to maybe in the past you've seen simplification of resistor networks with capacitors. It's very, very similar, but one minor difference. So in parallel, so parallel C's, CEQ is just the sum of the C components. Now for series capacitors, the equivalent is very similar to how you would find parallel resistors. Okay, so it's going to be the sum of 1 over the C component, and that whole thing to the power of -1. Okay, so to start this off, let's identify sections that we could simplify rather easily first. Okay, so here we have these 3 series capacitors. So the CEQ, let's call the CEQ1. This will be equal to, well, they're all the same. They're all 14. So it's going to be like 3 multiplied by 1 over 14 microfarads to the power of -1. Okay, so it's going to be, just from quick math, 14 over 3 divide 3, and that's going to be 4.67 microfarads. And that makes sense because capacitors in series will have lower capacitance than any one of their components, and all of them are 14, so it should be less than that. I'm pretty sure that's 1/3 of 14, so that's another interesting thing. So if we want to redraw the circuit, we can redraw it like this. I'll copy over what we have that can stay. Like that. Copy that. Paste it down here. Now this is a pretty repetitive process, but this is quite important. Quite important. Okay. Okay, so we replace this entire like triple series capacitors with a single capacitor like this. 4.67 microfarads, like that. Okay, now here, let's do this in a different color. We got a couple blues. So this will be parallel. CEQ is just going to be 14 microfarads plus 4.67 microfarads. Equivalent parallel capacitors, those are nice and easy, so this will just be 18.67 microfarads. Okay, so to redraw our circuit one more time, we're going to have something like this, 106 volts. Here we're going to have 11 microfarads, 14 microfarads. On the top was also 14. And over here we have 18.67 microfarads. Okay, now let's do a different color, green. You know, it is a very progressive process, but there's nothing to be worried about. You can see here in green, we have series. Okay, I'm going to just zoom out a bit and extend the vertical length of my page. Maybe I'll just move everything upwards like that. Okay, cool. So back to business here. So our series here is going to be CEQ. So we're going to need to add up all the inverses. So we have 1 over 14. Then we have 1 over 18.67 microfarads plus another 1 over 14. Whole thing to the power negative 1, meaning just like 1 divided by it. Okay, so we got, let's do that math real fast. So 14 to the power negative 1 plus 18.67 to the power negative 1 plus 14 to the power negative 1. Close the bracket, everything else to the power negative 1. And here our result is 5.09 microfarads. Okay, so our final thing here, do we have a, okay, we don't have a solution there to verify, but that's cool. So the circuit drawn one more time. This will be the last time we redraw it. This will be 160, 106 volts. Here we got 11 microfarads. Here we got 5.09 microfarads. And as we can see, well, the CEQ of this one, let's put that in red, is really just going to be 11 microfarads plus 5.09 microfarads, which is just CEQ of the whole circuit is just 16.09 microfarads. Okay, so okay, I lied when I said this will be the final redraw, but this is like the actual final redraw. So 106 volts and 16.09 microfarads. Okay, so this is the final equivalent capacitance. See, it's really nothing particularly that's too difficult, but you know, there are a lot of steps involved, and you have to be very precise when you traverse through every step, because if you make an error in step 1, like if we made a mistake when like on the first part of our sequence here, like it would crash the boat for the rest of it. So you have to be very precise and double check before moving on, because if you find an error in your calculations deep like much later, it's going to be painful to try to track down what caused it earlier on. Okay, now the second part of our question, just to get a little bit more space, we'll get up here, is asking us, what is the charge on the 11 microfarad capacitor centered between Y and Z? Okay, so pretty much what we know here is that we have what it's pretty much asking us is we have our voltage source here, 106 volts. Here we have 11 microfarads, and here we have like a whole other of circuit, which is not really particularly relevant for this. We are looking for the charge on just the 11 volter. Okay, now the reason why the other part of the circuit is not really relevant is because we know that the voltage is always the same for the rest of the circuit, right? So the voltage between YZ, so VYZ, actually I'll do ZY instead to make it a little bit more formal. This is equal to 106 volts. Okay, so you know, as it's very clear on the voltage source side, we know that there also has to be 106 volts of difference across the capacitor and across like the whole right side of the circuit here, which is not particularly relevant. That's going to be 106 volts as well. Okay, now we know that the charge on capacitor, charge of capacitor equation looks like this. So we have Q equals CV. Okay, so we're pretty much just trying to solve for Q, because it's asking us the charge. Q is the charge, so we just got to multiply 11 microfarads. So Q equals 11 times 10 to the negative 6 farads multiplied by 106 volts. And that should give us the voltage, I mean, not the voltage, that should give us the charge on the capacitor. So let's ask our calculator. 11 times 10 to the power of negative 6. Multiply that whole thing by 106. And we get our charge is equal to 0.00117 coulombs. And 1, 2, 3. Another way we can write that is 1.17 microcoulombs. All right, so micro is the same as 10 to the negative 3, so that's pretty much what we got here. So this would be the charge on 11 microfarad capacitor, and that would be awesome. Okay, so that would be how you find the charge on the capacitor. Q equals CV. Don't forget that equation. Capacitor charge. It's a pretty nice equation. Can't lie. Okay, cool. So that pretty much concludes this this question. Yeah, awesome. So is no given solution to verify appears blank to me. Cool, so I would love to answer this question, but we are kind of getting tight on time here. So I do need to wrap this up here. Okay, let me switch over to my screen real fast so I can mention a few things. So those are all the questions that we have for today. If you enjoyed today's Q&A and would like to be notified of when we have our next live stream, please hit the subscribe button and ring the notification bell. If you would like to submit your own questions, check out the links in the video description below. Remember to leave a like and a comment, and if you really like the video, share this video with your friends. This has been Millan from OneClass. I hope to see you again soon for more fun with physics, math, and everything in between. Had a great time. Physics is always fun, and I hope you have an amazing rest of your day. And don't forget to stay safe and enjoy the physics.